Okay, good afternoon, everyone. I'm Yuanfu Luo from National University of Singapore. I'm going to present important sampling for online planning and uncertainty. Automatic planning is an essential component of many intelligent systems. However, robots in the real world often need to plan with uncertainty. For example, the imperfect control for the flying drone, the unknown positions of the objects for the grasping robots, and the unknown positions of the other vehicles for the autonomous car, and the noisy sensor readings for the demanding robots. Uncertainty makes planning much harder. A general way for planning under uncertainty is to search in a belief tree. Each node represents a belief, the probability distribution over the world. The agent begins with initial belief B0, and it has many action choices. Executing an action can lead to different observations, and conditioned on the action and observation, it reaches the new belief and then replans a new action. The objective is to maximize the total discounted reward by choosing the actions in different time steps. And Bellman's principle of optimality tells us we need to maximize the immediate reward plus the reward in the future. And the future reward considers all possible future observations because they are uncertain. However, searching in a belief tree is computationally expensive because of the big tree size. Here, A is the action space, and D is the planning horizon, and O is the observation space. For many tasks, observation space is very large. Think of autonomous car driving, and the observation is all the possible sensor readings, which is really huge. So, to deal with the very large search tree, I'm going to make use of a very general idea. Let's think of uncertainty as just many possible future scenarios. Maybe it's possible to make the right decision by considering a representative subset of the scenario instead of all. So we represent the scenario as a sequence of a random number. A random number determines the uncertain outcome of a given action. Hence, given an action sequence, a scenario determines a unique path in the tree, and which consists of the observation states and the action encountered. And different action sequences can lead to different paths in the tree. And given another scenario, we can obtain another set of paths. And we do it for k scenarios. Then overlay all the paths together, we can get a sparse tree, which we call DESPOT. And then we can search in this tree for the best action to execute by evaluating the actions on the sampled scenarios. This is really a very simple algorithm. You sample a set of random number sequences, and that results in a tree. And then you can use any standard tree search algorithm to search the best action at the root node of the tree, according to the Bellman's principle. So this figure shows an example of DESPOT with height 2 and constructed with 2 scenarios. And by sampling scenarios, DESPOT successfully decreased the exponential term in the full belief tree to a number of scenarios and reaching a same level complexity with deterministic planning, which is much smaller than searching in a full belief tree. So DESPOT has been applied to autonomous driving a car, and the car can drive near pedestrians safely, smoothly, and efficiently in the real-world running. However, in simulation with a very small probability, it still collides with the pedestrians. The reason is DESPOT fails to sample the collision event, which makes the car drive aggressively and finally results in the collision. Collision with pedestrian is a rare event, but can lead to significant consequence, hence it's critical. The planner needs to sample such critical rare event to avoid a suboptimal policy. So what makes DESPOT fail to sample such critical rare events? In DESPOT, the events are sampled according to their natural probability of occurrence, and the algorithm doesn't care about how important the event is. For example, this path may have some small probability event, hence it's not easy to be sampled, but at the end of this path, some event with high reward or high penalty may occur, and if we fail to sample this path, the value estimation of this path will be inaccurate, hence it may cause a suboptimal policy. So to address this issue, instead of doing standard multicolor sampling, we do important sampling, which means intuitively we increase the probability of sampling the path that is important. So let's first look at how the path is sampled. We first sample a state from the initial belief, and executing the given action leads to the observation and next state, so on and so forth. And when using standard Monte Carlo sampling, the observation and the state at each time step is sampled according to their natural probability of occurrence, which is from the distribution P. But when using importance sampling, we use another distribution Q for sampling, and then we reweight the samples by W, and we call the Q function as importance distribution, and we need to design this Q function to make it capture the importance of the path. And we will talk about how to design this Q function in the later slides. Before that, let's first look at the performance guarantee of our algorithm. So V pi here is the true value of executing a policy pi. V pi hat is our estimator, and the second term here is the approximation arrow. It grows logarithmically with the action space and observation space, indicating that our algorithm scales up well for tasks with very large action or observation spaces. And our theorem holds for any importance distribution. So the theorem only tells us the performance guarantee, but doesn't show how to select an importance distribution. So how to do that? To answer that question, let's first look at this figure. So you want to estimate the expectation of Fs, where S follows a distribution P. Then a simple idea is that we can sample many S from P and then average their values. Importance sampling theorem tells us if we sample more points in the area, in the green area where Fs is high, it helps to decrease the estimation variance. But in DESPOT, a sample S corresponds to a state sampled according to the initial belief, and its value Fs is the expected reward given a starting state S following a policy pi. The problem is that we don't know this value exactly, and we can only do Monte Carlo simulation to estimate this value, and the variance of estimating this value also brings errors. So in such case, we prove that we need to sample more in the area either Fs is high or its estimation variance is high, which is in the green area or the red area. Here, the variance is high. Okay, so formally, we prove that the optimal importance distribution has the following form, the Q star, and it gives the state increased probability of being sampled when either the mean or the variance is high. So to use this Q star, we need to know the mean and the variance, but the problem is that we don't know either of them. So how do we solve this? One solution is that we can approximate them by learning from offline DESPOT runs. So our procedure is as follows. We first collect data from offline DESPOT runs, which is the state and value pairs, and then we construct F, the mapping from state to feature. We do this because state space is usually large, and we need compact representation of the state. So we use the feature to represent the state. And then we learn the mean and the variance for the features instead of the state. And finally, we construct the Q star using the learned mean and the variance. Okay, we did 5 experiments, and we proved that our algorithm can handle tasks with critical rare events, including, in particular, these 2 large-scale problems. Their state space is very, very large. And we compared our algorithm with POM-CP and DESPOT. There are 2 state-of-the-art online algorithms for planning and uncertainty. And the tables here are the total rewards we get for each task. And our algorithm significantly outperformed POM-CP and DESPOT for 4 of the tasks, which contains critical rare events. And for this task, rock sample, it doesn't have critical rare event, hence we didn't get improvements. I'm sure most of you are familiar with the video game Pac-Man, and this task called Pac-Man is an adaptation of this game. And in the Pac-Man, the agent can see the whole world. But in the Pokemon, the agent only see part of the world. And our algorithm outperform both POMCP and DESPOT. We also try to manually construct the importance distribution instead of learning it. But this performance is not better than POMCP and DESPOT. This is because designing an importance distribution for such a complex task is not easy. And we applied DESPOT and our algorithm to autonomous driving in a cloud. Those pedestrian data are all recorded from real world, from the campus scenario. And the left video shows the experiments using DESPOT. And in this experiment, the car drives very aggressively, and it finally collides with the pedestrian. It collides with the pedestrian, but I'm not sure what's wrong with the video, but it will collide with it. So we think this is because DESPOT failed to sample the collision event. And in our new algorithm, we increase the probability of sampling this event. And this time, the planner successfully sampled the collision event, and it plans a better policy to avoid the collision. What's wrong with this video? Sorry about that. And this in this time, in DESPOT, the car collides with the pedestrian, but in our new algorithm, it doesn't collide with the pedestrian. But there's something wrong with the video. Sorry for that. In summary, we propose a new algorithm for large-scale online planning and uncertainty in real time, and we use importance sampling to handle critical real events for robust performance. And there are many directions for us to extend our work. First, we can consider importance sampling for large observation spaces. And second, the idea of importance sampling is general. We can apply it to other simulation-based planners for planning and uncertainty. And one limitation in our current work is we need to manually construct the features, and we want to fully automate the importance distribution construction through the feature learning in the future. Thanks.
Thank you. Okay, our first commenter is Marco. There we go.
Sorry, can you?
So what policy do you use to compute the sampling distribution, the Q?
So we use a very simple idea. Simple idea. We just learn we first manually select a feature, and then we collect the state and the value pairs. Then we discretize this to use a directly discretized mapping.
Okay, because usually when you use importance sampling, you try to leverage some problem-specific knowledge of how you encounter critical states. It was unclear to me what type of knowledge about the problem you were exploiting in order to come up with this good importance sampling distribution.
So you mean we can incorporate the domain knowledge into?
Yeah. So is Q learned on the same problem instance or different ones?
For each task, we need to learn one important distribution.
Okay. Maybe the other presenter can plug in, and we'll take a couple more questions. Yeah.
So great talk. Well, one question I have is that in some like Monte Carlo tree search algorithms, you expand nodes that are going to lead to a higher reward or higher expected reward. How would you bias your estimation of critical rare events towards those that are likely to affect the rewards?
Sorry, can you?
So
say your questions in one sentence?
So it looks like the way that you're sampling is sort of agnostic to whether that state and action pair will the reward received by that state and action pair, right? And I'm sort of curious, like, if you use the reward function to figure out where to sample, how would that change anything?
Use the reward function to.
Well,
So I think, let me see if I can
Yeah.
interpret a little bit. It seems like there might be an opportunity to combine your insights and the insights of POMCP to use both value and sort of idea about the likelihood of an important event happening down a branch. So have you thought about combining both of those ideas in some sense?
No.
Okay, that's exactly what I was trying.
Okay, good. All right, I think we should thank the speaker.